Hello, welcome to integration by parts using U substitution. My name is Cynthia and let's start. First off, we have an easy problem right here. So we have the integral of dx over x squared rad 4 minus x squared. So before we start drawing a triangle and execute the integral, we first need to remember to put the Pythagorean identity. And the way that this term under the radical has been specified looks like it would be in terms of one of the legs in the Pythagorean identity. So it would be a is equal to rad c squared minus b squared. And since both 4 and x are perfect squares, you can tell that x would be b and c would be equal to 2. Now drawing the triangle and putting all the terms in the correct places, we have to figure out which of the terms are we going to use. The most easiest ones to use are sine, secant, and tangent. We decided to use sine, so we set x is equal to 2 sine theta, and then we took dx of that. The reason why we took the dx is because we need to have a term that we can substitute in for dx, which is usually what people forget to do. Now we substitute in all of the relevant terms. So dx to cosine d theta. X squared is just our x term squared. And then for rad 4 minus x squared, it's 2 sine theta. But wait, why does it say 2 cosine theta? That's because you have to substitute in 2 sine theta into x. Looking over here, as we have substituted out and we have squared this term, and then we have factored out the 4, 1 minus sine squared theta is part of the identity of cosine squared theta plus sine squared theta is equal to 1. So we change it into cosine squared theta. Now we have two terms that are perfect squares and it gets rid of the rad. So we get 2 cosine theta. Now looking over here, we can see that after simplifying the rad, we have 2 like terms which will be cancelled out, and we just have integral of d theta over 2 squared sine squared theta. So continuing on, we take out the 1 over 4 and we bring the sine squared theta up to get cosecant squared theta. And the integral of cosecant squared theta is cotangent theta. But the answer isn't done over here because the integral originally given was in terms of x, not theta. So if you stopped at this point, your answer is wrong. You have to refer back to your triangle and see what your cotangent theta is. So since cotangent theta is the reciprocal of tangent theta, so instead of x over rad 4 minus x squared is rad 4 minus x squared over x plus c. So going towards the second example, we have rad x squared plus 2x dx. In order to be able to use trig, we should always seek to make sure that the term under the radical is a perfect square or a complete square. So since it's not, we will be completing the square and we will get x plus 1 squared minus 1. And that's what we substitute in for this term down there. Now that we have a difference of squares, because 1 is 1 squared, we can use the triangle and draw the triangle. Now referring again back to the Pythagorean identity, we can tell that this term is actually in terms of one of the legs of the triangle. So it will be b or a is equal to rad c squared minus a squared or b squared, depending on which leg you want to reference. And as you can see, 1 is squared, therefore c would be x plus 1 and a would be 1 in this scenario, which is placed in the relevant sites. Now it gets a little bit tricky here because we have it in terms of secant and tangent, but you can still be able to solve this problem if you really think about which terms you want to substitute in for this term and dx. So we have chosen secant theta, and secant theta is equal to x plus 1. Remember, secant theta is 1 over cosine theta. Then we take derivative of both sides, we get secant theta tangent theta d theta. And that is what will be substituted in for dx. Do not forget to have a term to substitute in for dx. Very important. Then tangent theta would be for the actual radical term. And then we get integral of tan squared theta secant theta d theta. The reason why tan is squared is because you have two tangents here. Now looking at the integral of tan squared theta secant theta d theta, first we can identify that tan squared theta is part of a trig identity. So we use it and we get secant squared theta minus 1 parentheses secant theta d theta. And we distribute the secant theta. So now we have a simple integral of secant theta d theta which can be easily solved, but we have this really complex secant cubed theta d theta. So what we do is that we take it aside and we integrate it. So we split the secant squared theta, secant cubed theta to secant squared theta and secant theta d theta. And we use integration by parts. For this integration by parts, u was chosen to be secant theta, du was chosen to be secant theta tangent theta d theta. And dv was secant squared theta d theta, which would give us a simple term of tangent theta, and it's not going to be squared. Now here's a really good hint. If you cannot remember this formula, if you put your u's and v's in this order, du's and dv's as well, then you can just circle around, just like a 7, a stroke of a 7, and you will get the first two terms. So uv secant theta tangent theta minus integral of v du, which is right here. You have two tangents, so that's why tangent is squared. So now you can see that the first half of this integral does not need any integration. But the second half you're stuck with another integral. So you take that aside and you start integrating again. So you have tangent squared theta secant theta. You use the trig identity again. You end up with secant squared theta minus 1 secant theta d theta. Now as you can see, we started off with secant cubed theta d theta. We ended up with it too. So what do we do in that scenario? We set the original equation equal to the integral of the entire term. So secant theta tangent theta, right here, plus, or you can have it minus, and then these two terms would have to be positive. So secant theta tangent theta minus the integral of secant cubed theta d theta plus secant theta d theta. So these two terms are this term. Now looking closely at the equality that we came up with, we can see that we have two secant cubed thetas d thetas, so you add them to one side, so that integral is on one side and the rest are on the other side. Integral of secant theta d theta is known to be ln absolute value of secant theta plus tangent theta. Then we divide both sides by 2, which is where this half came from, and that is the integral of secant cubed theta d theta. Looking back at our original integral, after we had integrated tangent squared theta secant theta d theta, you can see that we had a secant cubed theta d theta that was really complex and we didn't know what the integral of it was. So far, all the steps have been to find what secant cubed theta d theta is. Now that we have that, we can easily integrate it. So secant cubed theta d theta is right here, and a step prior we figured out what integral of secant theta d theta is, and you subtract it. But there's also a last step. Remember that the integral that you started with was in terms of x's, not thetas. So if you leave it in terms of thetas, you will get the wrong answer. So substitute in the respected trig identities the respected trigs, and you should be able to get the answer. And do not forget the plus C. Thank you very much, and have a wonderful day.